right, good morning, everybody. It is a pleasure to be here with you. This has been a fantastic conference. I want to thank all the presenters that have gone on before, and of course, Mike, who's done a great job putting this all together. I am Ben Curtis. I am from Seattle-ish. I actually live in Kirkland, and that doesn't matter to anybody who lives outside of Seattle. But if you do live in Seattle, and I say I'm from Seattle, then that's totally false. So I have to be clear about that. I am one of the co-founders of honeybadger.io with Starhorn and Joshua Wood. And if you don't know about Honey Badger, you really should, so go check it out. It's an awesome service for Ruby developers. And you can find me at Stimpy on the interwebs. I'm excited to be talking about this topic, about machine learning techniques. It's been fun to put together this material, and I hope that we can spend a few productive minutes together talking about it. I will apologize if you are a machine learning expert, because I am not, but I do enjoy this topic, and I hope that I won't offend you by the things that I say that are wrong. You can correct me later, and if I mislead any of you, I apologize sincerely. So we're going to learn about machine learning. It's kind of a big topic, so I'm not going to talk about all of it, and I'm not going to talk very deeply about it. But I want to talk about it from the approach of I'm a Ruby developer, and I want to know what this machine learning thing is about so I can see how I might use it in my applications. So that's the intent. If that's not interesting to you, you can go and do something else for half an hour. There is a lot of info out there. So once you start learning, you can just keep going and going and going and going. So if you feel intrigued by the things you learn here, you can definitely hit up Wikipedia and a bunch of other resources to find out more. But the main thing that I want to do today is I want to introduce you to a couple of the secret passphrases and keywords that you'll need to be able to actually have a productive line of research into machine learning if you want to learn more about it. The thing about machine learning is that it seems like this big, black, mysterious thing that you don't know anything about, and once you know a few keywords, then you can kind of get your foot in the door and go from there. So we're going to talk about what some of those few keywords are, and that'll help you on your journey to finding the right pattern or algorithm to help you in your quest. So the other title that this talk could be is making sense of a bunch of data. And that's really all machine learning is to me, from my viewpoint, is helping me deal with the gobs and gobs of data that I have coming in and making some smart decisions about it or learning some interesting things from it. Before I dive into the talk, though, I want to have, of course, a warm-up joke. And I haven't seen any of these so far in the presentation, so I'm glad I can be the first. And here it is. I love that joke. It's so awesome. I was sharing that with my family over dinner the other night, and I had to explain what TCP and UDP were. And I love my kids. They're great. They humor me, and it's a lot of fun. Okay. Before we get into machine learning and what you can do with all the fun data that you're going to have, you got to have some fun data. And so logging is important. There's a great blog post written by a fellow by the name of Jay Krebs, works at LinkedIn, and this is from December, and he talks about setting up a logging infrastructure inside your business to capture all the information that you have. He did this at LinkedIn, so you can imagine that that's kind of a big job. But he talks about why logging is so important, and it's not just about storing strings to text files that someone might grep through later because there's a problem. That's maybe like your first order of logging, but think a little more abstract than that. Think about all the data that comes into your enterprise, into your application, passes through it, and what is happening to all that data? You're just throwing it away because you're not tracking it, or are you finding some way to systematically log it, and so you can analyze it later. And that's kind of the first, I guess, a step zero of machine learning is first having a bunch of data to learn with. Sometimes we forget that when we're dealing with data, the when can be as important as the what. Especially when we talk about recommendation systems and freshness, the when of things happening it can be very critical. And if you don't log, then you don't know when things happened. So to help you in your logging endeavors, here are a few products that you might look into to get started on having a way to log all the things that are happening in your environment. I am most familiar with Logstash, which works well with Elasticsearch, and Kibana for visualization. But these other systems are great too. Amazon would happily let you use their system if you feel like paying them for that. But all of these are great. Apache Kafka was written by Jay Krebs, who talks about logging, so it's a pretty intense thing. And of course, with any Apache project, there's a lot of stuff to go along with it. So take your pick. Okay, so let's talk about clustering. We have a lot of data. We want to make some sense out of this data. So let's make it into smaller piles of data. Machine learning is a lot about sifting through all this data that you have and breaking it up into parts that you can actually understand something about that data. Taking the clustering approach says, okay, let me analyze everything and see if I can start looking for patterns. The principal thing that you'll find, algorithm that you'll find when you start thinking about clustering is K-means clustering. Now, we were introduced yesterday to what K is, and you might know what a mean is. That's just simply an average. And so we take averages of things, and we're putting them into K buckets, all right? So K-means clustering just says, okay, given a bunch of points, and usually we're talking about Cartesian points. It's not limited to just that, but typically we're talking about anything you can graph on an XY plane. Given a whole bunch of these things, let's cluster them so that we can identify which ones are similar and which ones are dissimilar. This is very useful in mapping applications, obviously, and we'll talk about that in a minute. But basically, we want to take n observations and divide them into K clusters. And the K-means clustering has one significant drawback, and that is you have to decide what K is. But that's what is a shortcut that actually makes it work pretty well. So if you don't have any problems deciding what the K is, K-means clustering is a great thing. In the terms of machine learning, this is a K-means clustering. All clustering techniques are kind of what's called unsupervised learning. We're letting the computer decide what it wants to do with the data without giving it much or any guidance. So let's have a demo. Here's my demo, courtesy of Wikipedia. If you go to the Wikipedia page, you can see this fantastic demo, but here's how K-means works. We have a series of points here. So these are all points in our data, and we're going to say we want a K of 3. And given this set of data, let's pick 3 points at random. This is actually one of the initialization methods you can use, but it's a good one. And given those random 3 points in our data, let's say those are our clusters that we're going to start with. Once we've identified our centroids, we now need to look and decide which of our other data points are close to those centroids. We do that by taking the average of the xy distance to those centroids. And on the first pass, we say, oh, okay, it looks like that top one is near the top centroid, and so on and so forth. Once we've identified this initial set, then we move the centroids to a position that is at the center of that set. We now repeat that process. And we say, okay, now which points are nearest to the centroids? And as we go through that process, we find that these are our clusters. It's a pretty straightforward process. You can do this visually if you have a small data set. It takes not too long, and comparatively speaking, and it works pretty well. Basically, you know you're done when the points stop moving. Here's the canonical example. Let's say we are building an application where we want to plot a bunch of points on a map. This is a screenshot from Zillow, and they want to plot a bunch of houses on a map. The problem comes when we want to zoom out. So a naive implementation of a map would say, okay, I'll show you all the points that are in the map area. And then all of a sudden, that's not helpful at all. What do? You cluster. So instead of showing 500 points or 5,000 points, you cluster those 500 or 5,000 points into 5 or 6 clusters, and then you show the clusters with the counts. And then, of course, you've seen this. You click on a cluster, you dive in, and you see the exploded view. This is pretty straightforward, and it works really well. There's actually a client side, more than one, but you might find MarkerCluster when you go looking for this sort of thing, if you need to plot a bunch of spots on a map. And that works on the client side, which is great if you only have a few hundred or so points. But if you have a few more, then you need to do some clustering on the server side, and so you can use some Ruby. So these slides that look like this have the GitHub repository as a title and the example code from the repository on the code part. So none of this code is mine. All this code is the original authors. So thank you very much, original authors, for making this easier for me. But look at the Kmeans gem if you're interested in doing some clustering. And here's pretty straightforward. Our first set of data there, we have a bunch of points on our plane, and we shove all these points into a new object, and we tell them how many centroids we want to have, or how many clusters we want to have. And then it gives us the same sets of points broken up into those clusters. Pretty easy. If you have a whole lot of points, this can get kind of slow. So this is a good opportunity for using some of the C that you learned yesterday and putting this out into a C library and calling it that way. My co-founder, Star, and I, we worked at alphaspace.com a while back, and this is exactly what we did. When we had to do a lot of clustering of points, he wrote some C code, and it was great. So after we talk about a bunch of data, and we've maybe clustered it so that we can identify it better, let's actually take some action on some of our data. And this is where we get into what's called supervised learning in the machine learning world. And that just means that we're going to give the computers some hints about how it should treat the data. And the first kind of supervised learning I want to talk about is decision trees. Ilya is fantastic. If you're not familiar with Ilya, you should definitely check out his blog at Igvita. He is just a genius, I guess, and he has written a bunch of code, and decision tree is one of the things that he's written. A decision tree is pretty simple, can be pretty simple. It looks a lot like a case statement. And basically, we say, you know what, we know that the ranges of things that we're dealing with, in this case, temperature observations, we know that certain temperatures have certain classifications, healthy or sick, and so we just teach the computer, okay, here are the classifications that we know about. Please just look at all the data, and you tell me what each one should be classified as based on this rule set that I give you. It's pretty straightforward, but you'd be surprised at how much you can actually do with this sort of thing. For example, you can have the computer write you an article that shows up in the Los Angeles Times. So on Monday, you may be aware there was an earthquake in California, and within 20 minutes of the earthquake happening, this article was published at the LA Times, and you'll notice that bolded line down the bottom, that highlighting is mine. That acknowledges that, yes, this article is actually written by a machine with some guidance from the author. So this guy is brilliant. He says, hey, I can make the computer do my work for me, and I can have it write my article. This is the same, if you were reading TechCrunch this week, this is the same earthquake that caused the newscasters to dive under the desk because it was kind of, check it out, it's kind of fun. But you'll notice in this article there are some places where a decision tree could have been used. I don't know exactly how he did this, but like the first sentence, a shallow magnitude 2.7 earthquake. How do we know it's shallow? That could be a decision tree, right? Whatever the magnitude is, let's say it's shallow or it's not, or what the depth of it was or not. It was 4 miles from Westwood. Okay, that's obviously some computation there happening with some great circle distance. It had a large swath. Well, what's a large swath? Okay, well, if the range is greater than 50 miles where it's felt, that's a large swath. Or if it's less than 10 miles, maybe that was very localized. Anyway, you can see that you can use a decision tree to put in a bunch of text. And I find this incredibly useful as a web application person by saying, hey, I can look at my user's data and I can say, if this threshold is under here, and I can send this kind of email versus that kind of email, or in that email I can put this kind of content versus that kind of content. So it's pretty easy to see how this can be useful to customizing content and making a better experience for your users. So decision trees are great, but they're pretty simple. So we want to get up to the next level, and that would be classifying. I love Munchkin. I play it with my kids, so I had to throw it in there. You might recognize that from the instructions in Munchkin. Classifiers. You're probably already familiar with some. You've probably gotten spam. So you are familiar with Bayesian classifiers. So a lot of spam filters are built upon Bayesian classifiers. It's just a way to say, what is this blob of text? Is it this or is it that? And again, this is supervised learning, so we are training the machine. This is that, and this is something else. And so we talk about having a corpus of data, and Aaron talked about it yesterday where he had his corpus of images. And so we train the machine, this is spam, this is spam, this is spam, this is spam, this is not spam, this is spam, this is spam, this is spam. And then over time, the machine's like, oh, I get it, this is spam, right? And so we train it over time, and they get better as we give them more of a corpus. We call this, you may have seen the naive Bayesian filter. It's naive because it just makes some assumptions that make the calculations easier. You can dive into that. You can use Bayesian classifiers for sentiment analysis. Let's say, I don't know if you've ever checked out the reviews on Amazon, but you may have noticed that some are positive and some are negative. And it might actually give you the thing that says, here are the most positive reviews and here are most negative reviews. Well, you can use Bayesian classifiers to decide if a review is positive or it's negative based on the words that are being used. Like, I hated this product. Okay, that's probably negative. Or, I love this product. It made me rich. You know, it's probably a positive review. And so you can classify things like that. Here's an example of a classifier. It's pretty straightforward. You say what your classifications are. In this case, something is interesting or it's not interesting. And then here's my corpus. Computer, this is interesting. Here's some other stuff that's not interesting. Now, some point later, I can say, okay, here's some unidentified text. Tell me if it's interesting or not. If you want to go up a little bit from there, there's another algorithm called latent semantic indexing, and or latent semantic analysis, if you prefer. And this particular algorithm is actually patented, which is awesome. And in fact, it can be used and has been used to discover prior art for patents. Surprise, surprise. Basically, what we do here is we throw a bunch of text at the classifier, and it looks at the text, and we say, okay, this is about something, or this is about something else. And what it can do, using the power of math and vectors, which we learned about earlier, it says, okay, this section of text has these kinds of words in it, and this block of text has these words in it, and based on the co-occurrence of those words in these two documents are similar or they're dissimilar. It doesn't know what these documents mean, per se. It doesn't understand like a human does, but it can say, okay, all these documents here about Amazon.com, and all these documents over here about Amazon the river. Okay? In Postgres, there's an example of this TS vector, if you're interested in fuzzy search, that does this sort of thing. But in the Ruby land, we have, again, the classifier gem. If you scroll down the GitHub page a little bit, you get down to the LSI part. And we just have a bunch of documents that we're sending to the classifier. And these documents have a bunch of text in them. And we identify, we tell, again, supervised learning, so we tell the machine, this is about dogs, or this is about cats, or birds. And then we say, okay, this find related thing, that's where I was talking about. It knows that documents are similar based on the content in them. Doesn't know what they mean necessarily, but it knows they are similar. So they can say, okay, given this new text, can you find me some similar things to it, like a prior patent search, for example. Or you can also ask the classifier, okay, here's some new text. Based on the classifications I've given you before, can you tell me what you think it's more like? Is it more like a dog or is it more like a cat? Okay, so once we have a bunch of classifications, once we've taught the machine a thing or two about our domain, now we can start asking it questions to give us more insight into the data that we have. We can ask it to recommend things. And this is a lot of time where people love to go when they talk about machine learning. You may have seen some recommendations on some popular shopping sites like Amazon. And the thing that's fun about interacting with websites that are having recommendation systems built into them is that we as customers are classifying ourselves, right? I'm buying this book on Python, or I'm looking at this movie, or whatever. I'm buying some garden supplies. And so I'm adding all these data points that classify who I am. And then Amazon can look at these data points and say, oh, well, based on what you're shopping for, what you looked at, or what your friends have bought, or whatever they use, I can recommend these things which I know are similar to you, or which have been liked or similar to other people who are like you. So the next time you're buying stuff, you can think, oh, I'm classifying. I'm doing machine learning. One algorithm is the Jacquard Index. So this is kind of a fun one. This is where it takes, it looks at discrete discrete sets of data, and it says how similar or different are these sets of data. And it looks at the unions and the intersections of these sets of data and decide how similar they are. It sounds similar to the LSI. Basically, it says, given, let's just look at the code. Given a few arrays, this is the Jacquard, one of the gems you can use. Given a few arrays, which ones are like the others? Now, we can see that, user A likes jeans and likes blue. User B likes jeans, likes apples, and likes red. So they're not terribly similar, because the union of those two arrays combined with the size of those two arrays is not a great ratio. But if you look at user C, he likes apples and he likes red. If you compare B and C, you're like, oh, you know what? B and C have a big union, and also that union is as big, is very similar to the total size of those sets. So these guys are pretty similar. And the Jacquard will tell you the coefficient of the similarity. So you can say, okay, given a new set of likes, how similar is it to someone else who's already in the system? The Kmeans library that I talked about at the beginning can also use the Jacquard Index as one of its calculations. So again, remember, means is only talking about averages, so xy is one way, but the Jacquard coefficient is another number that it can use as a measure for clustering people. So you can cluster people based on preferences, which is kind of fun. This library also, there's also a Postgres extension for this called PG Similarity, so you can calculate this stuff in the database, like Aaron was talking about yesterday with the function that did the Hamming distance in SQLite. That particular Postgres extension has Jacquard, it has Hamming, and so if you're doing a lot of computations over a lot of data, putting in a database can help your performance quite a bit. There's another useful gem called Recommendable, which takes these concepts, especially Jacquard, and says, okay, let's let a user like something. So I'd say I'm doing a movie site, and I want my users to like movies, and after they like a certain set of movies, then I should be able to give them recommendations on what movies they might like that they haven't seen yet. So if I like movie A and I like movie B, then then I know that Alice has also liked movie A and movie B, and she's also liked movie C. Well, then there's some reasonable assumption that I might also like movie C because our likes are similar. So the recommendation system can say, Ben, you should check out movie C because other people who are like you have liked it. This recommendable gem is pretty cool. If you're familiar with Redis, you might be thinking, hey, that'd be a great place to put stuff because it deals with sets all the time. And in fact, this gem uses Redis to store those sets, so it's pretty quick. You can also, this gem is neat also because it has an idea of the nearest neighbor, which if you've done much plotting, can tell you how relevant something is or not. And so you can actually limit it to a certain number of people to help refine the recommendations. It does all kind of fun stuff like that. But if you check out that gem, there's a blog post that this author has written that goes along with it that talks about it in great length, and it's a good read. If you're really interested in recommendation engines, and especially if you're doing e-commerce-like things, you should definitely check out this ebook by O'Reilly called Practical Machine Learning. It is a free resource. All you have to do is give up your email address so they can be marketed out for the rest of eternity. But once you've done that, you get access to this great book, and it talks about using Apache Mahat and Apache Solr. And the approach that this author takes, I find really intriguing. If you classify people based on their likes, so let's say that you got 3 shoppers, right? And here's an example they use in the book. You've got Alice, and you got Bob, and you got Charles. And Alice likes apples, and Alice likes puppies, and Alice likes ponies. I got ponies in there. Charles, he likes ponies too, and bicycles. And Bob, he likes apples and ponies. They all like ponies. So what can we recommend to Bob based on the recommendations that other likes that are in the system? Well, ponies, what? Did someone give the answer? Ponies make no sense because everybody likes ponies, so we're not going to recommend to Bob that he likes ponies because everyone likes ponies. But we know that Alice has liked apples and puppies, and Bob has chosen to like puppies, and so he might also like apples. So that's the example they use in the book, and they talk about how Apache Mahat has algorithms built into it that allow you to feed all this kind of data into it, and then it can do similarities, it can look at co-occurrences, and it can say, oh, and it can ignore those universal ones like ponies, and then it can tell you, by the way, you should recommend puppies to someone who likes apples. And then he talks in the book about using those recommendations and putting them into Solr, which I think is really neat. So then if you have products, if you have the Apple product, you can say, in Solr, here's a list of related products like puppies, and conversely for puppies and apples if you want. And so it makes it really easy then to have a searchable index that you can use to look up like products or like documents or whatever. You can use your imagination to come up with interesting things. But I thought that was an interesting approach. And that is all I have. So I have a couple minutes.